Right. From the last session, if you recall, the hydrolysis, what we learned was about weak acid and strong base combined salt. So if a salt is made out of weak acid and strong base, then we realized that the conjugate base appearing from the weak acid will be having sufficient strength to break the water molecule, and that causes that hydrolysis, and which indeed increase the OH minus concentration of the solution. Okay. Hence, whatever the questions we attempted, we always notice that the pH value will be greater than 7 because the solution remains basic. Correct. Now is the second case which we will discuss. See, the second case is about HCl, which is a strong acid reacting with a weak base, and NH4Cl formation and water formation. This is what you will notice. Correct. See, unfortunately, I could not put a lot of space in here while making the pre-notes. I should have put more space for this notes, but that's okay. I would suggest, if you have extra page, use it. Otherwise, just try to write it in a very smaller, fonts. Got it? So let's see how we can solve the cases where you have a salt that is being derived from strong acid and weak base. Got it? So it is a strong acid and weak base case. Let's see. If you have this salt present, and I've been insisting you to understand one thing, that whenever we are talking about salt hydrolysis, the presumption is that there is no acid or there is no base left. Only salt is present. Okay. Of course, there is added in water, but otherwise, there is no acid base present in the solution. If that is the case, the first thing what you need to write is that NH4Cl in aqueous solution, because being a salt, you expect them to ionize completely, which means if the concentration is C naught here, salt concentration is C naught here, we know that this will completely get, you know, dissociated into formation of C naught and C naught. And now the NH4 plus is a conjugate acid which is very strong relative to the other acids, and it will have enough strength to hydrolyze water, which means the next thing you need to make is that how NH4 plus will interact with water, and the equilibrium constant for that is KH. It would give you NH4OH plus H plus. That's how it is breaking the water molecule into OH minus and H plus. So it is holding that OH minus and releasing away that H plus ions. Got it? So now you have the concentration initially as C naught. This was the initial concentration. As it reaches equilibrium, it will become C naught minus C naught H. What is H? I discussed that on the other day. H is, see, I'll write both the forms. KH is hydrolysis constant, while uh, H is degree of hydrolysis. Degree of hydrolysis. Okay, correct. And now, whatever the NH4OH which is forming, okay, that will also represent an equilibrium OH that will be in equilibrium with NH4 plus aqueous plus OH minus aqueous. That we call it as Kb, correct? Other than that, we also learned that the water H2O liquid will maintain its equilibrium as H plus aqueous and OH minus aqueous, and the respective equilibrium constant is Kw. Now, if you recall, we can write the Kh as C naught H multiplied by C naught H divided by C naught minus C naught H. The derivation is exactly same the way what we have done it earlier. So it will be C naught H square by 1 minus H. And for our practical purposes, H is always assumed to be far lesser than 1. That implies Kh is equal to C naught H square, or H is equal to under root of Kh by C naught. Okay. And on the other hand, we also know that Kh can be represented as concentration of NH4OH multiplied by H plus divided by NH4 plus. Correct. While Kb can be represented as concentration of NH4 plus into OH minus concentration divided by NH4OH. While Kw can be represented as H plus concentration into OH minus concentration. Now you can clearly make out that if I multiply Kh into Kh into Kb, it will lead to the formation of Kw. Okay. Now coming to the concentration, you know that H plus concentration in the equilibrium here suggests that it is equal to C naught H, which is equal to C naught into under root of Kh by C naught, which is equal to under root of Kh into C naught. And Kh we learned that as Kw by Kb into C naught. So thus, if you take the log on both sides, you will get minus log on both sides. You will get this as half of minus log of Kw minus log of Kb minus of log C naught. This is what you will get. And that leads to our final equation, which is pH is equal to half of pk pkw minus pkb minus log C naught. And this value always has to be less than 7. Got it? Because now the solution has become acidic. It has become more acidic. Clear? So hence, this should be the derivation for it. Please go through it once, everybody. If you have any problem, please let me know. I can discuss. And everybody, the formula is clear. If any of you are comfortable with these formulas, you have already learned it. Just make the note of the formula. We will why I mean just to make sure that you take the help of the formula to solve the questions. Check this. Let's try this question. 100 ml of 0.2 molar NH4OH is titrated with 200 ml of HCl. Find the resultant solution, correct? The pKb value of NH4OH given is 5. Okay, so let's see how we can solve that. It's clear to us that NH4OH plus HCl, when they are reacting, we expect it to form ammonium chloride plus H2O. The value wise, if you notice, it is 100 into zero point 0.2. Here it is 200 into zero point 0.1. So here it is 20 millimoles. Here also it is 20 millimoles. So none of this part will be left. Everything will be reacted to become 20 millimoles of ammonium chloride, and which means 20 millimoles implies the concentration of NH4Cl, which will be same as concentration of NH4 plus, is equal to 20 millimoles divided by total volume. In this case, the total volume is 300. So which makes it 1 by 15. That is the concentration of uh, NH4 plus, which we use the terminology as C naught. So by formula, pH is equal to half of pKw minus pKb minus log C naught. That is equal to half into pKw is 14 minus pKb is 5 minus log of C naught, which is 1 by 15. So that is half into 9 minus 9 minus, sorry, 9 plus log of 15. Log of 15 is log of 3 plus log of 5, so which is 0.48 plus 0.7. So that makes it 1.18. So 10 point, so which is equal to 10.18 divided by 2, so which is 5.09. So that is the pH of the solution. You can clearly notice that it is less than 7. Please do check if you understood this solving, how to figure out the pH of the resultant solution. Right. Next, notice weak acid plus weak base combinations. That means this time the salt formation that we are looking for is when you have a weak acid and a weak base combination. When you combine these two, the product, the salt which is formed, it is still being a salt. It will ionize completely. So if the initial concentration is C naught, it will ionize completely. Got it? But you got to understand one thing, that hydrolysis will take place because of CH3CO minus also and because of NH4 plus also. This is a strong base and this is a strong acid. Both will help in ionizing. Both will help in hydrolyzing the water molecule. Got it? Now listen, since both of them are present equally and both of them are present independently, we expect both of them will react with water like this. So if we have CH3COO minus plus NH4 plus, that together can react with water to take H plus towards acetate and OH minus towards NH4 plus. And this equilibrium constant is what we call it as hydrolysis constant in this case. And initially, if you notice the concentration, this is C naught, this is C naught, and nothing was formed. At equilibrium, now this will be C naught minus X, C naught minus. Now, this is the important part that we are taking it as an assumption. The assumption is the amount of hydrolysis which acetate can do, we are expecting the same amount of hydrolysis which NH4 plus can also do. If CH3CO minus is responsible for breaking 4 moles of water, I'm expecting NH4 plus will also be responsible for breaking 4 moles of water. This is the assumption. Hence, here also we take it as C naught minus X. So this will become X and X. If I write the same in terms of degree of hydrolysis, so I will write it as C naught minus C naught H, C naught H and C naught H. Okay. And now, if you notice, how do we write the KH value here? KH value will be equal to CH3COOH concentration multiplied by NH4OH concentration divided by CH3CO minus concentration into NH4 plus concentration. This is KH value. And KH in terms of concentration terms given is C naught H multiplied by C naught H divided by C naught minus C naught H whole square. So here in short it is C naught by H by C naught minus C naught H whole square. And you can clearly make out that the C naught is getting cancelled. So you will be only ending up with H by 1 minus H whole square. Or in short, H by 1 minus H will be equal to under root of K H. This is an important equation which will help in solving. So remember that H by 1 minus H is KH. And now let's see. Whatever the acid which is forming and whatever the base which is forming, they both will have their own ionizations. So acetic acid will ionize into the formation of CH3CO minus plus H plus. Likewise, NH4OH will also ionize into NH4 plus plus OH minus. And for this, this is Ka of acid, this is Kb of base. And Ka value can be written as concentration of CH3CO minus in the solution into H plus concentration of the solution divided by CH3COOH of the solution. Similarly, Kb will be equal to NH4 plus of the solution into OH minus of the solution divided by NH4OH of the solution. So we got what is KH, we got what is KB, and what is KA. What if I multiply all three? Check out. KH multiplied by KA multiplied by KB. What is left over? In KH and KH, this CH3OH and this CH3OH will get cancelled. NH4OH and this NH4OH will get cancelled. Okay. And then NH4 plus and NH4 plus will get cancelled. Then CH3CO minus and CH3CO minus will get cancelled. So in short, all the terms are getting cancelled except for H plus and OH minus. And for that we call this as KW. So which means KH for weak acid, weak base combined salt will be equal to KH into KW, KW by Ka into Kb. Okay, this is what you will get. KH value will be equal to KW by Ka into Kb. And now how do I calculate the H plus ion concentration? Okay, it doesn't seem to be like this has or this has any H plus or OH minus directly involved in the solution. Okay, but if you notice here there is H plus and here there is OH minus, I can use these terms. Let me show you how. You know that Ka value will be equal to CH3COOH. Sorry, let me directly take from here. Since Ka value is this much, I can write this as H plus concentration will be equal to CH3COOH concentration divided by CH3CO minus concentration into Ka. And CH3COOH concentration is approximately C naught H. And CH3CO minus is equal to C naught minus C naught H. So therefore, this is C naught into H divided by C naught minus C naught H into Ka. So C naught will get cancelled. So what do we left? H by 1 minus H into K. Do you realize we have got this value before? H by 1 by H can be written as under root of KH. That's what we will be using here. So H by 1 minus H is equal to root of KW, sorry, root of KH. So if I substitute that, so I will get H plus ion concentration is equal to root of KH multiplied by Ka. Now if I take Ka inside the root, it will become KH into Ka square. That is equal to KH we just derived it as, let me put this as equation 2. We derived the KH value as Kw by Ka multiplied by Kb, and now it is multiplied by Ka square. So 1 Ka will get cancelled. So we will get this as Kw into Ka divided by Kb. And now if I take the minus log on both sides, you will get pH. So pH is equal to half of minus log of Kw minus log of Ka, okay, and minus of minus of minus log of Kb. Got it? So this is equal to half of, this is pKw plus pKa minus pKb. Hence, this is the formula that you should be looking into. pH is equal to half of pKw plus pKa minus pKb. This is for weak acid plus weak base combined salt. What are the important takeaways from this derivation? One, right? If you may have noticed, the H plus concentration is now independent of initial concentration. Unlike the first two cases where H plus is dependent on what was the initial salt concentration, here H plus or pH is independent of initial salt concentration, which means you can take the salt as the concentrated part or you can take it into a dilute part. It does not make any difference. The pH will remain same. Okay. Second is that assumption. Okay. Assuming CH3CO minus and NH4 plus makes makes same amount of hydrolysis. Same amount of hydrolysis. Okay. So based on this assumption, we were able to derive this. Okay. So as long as the weak acid, weak base is concerned, whatever the data which is given, what is the initial concentration, it is irrelevant if you are calculating pH of the solution. Okay. So I would suggest all of you to go through it once thoroughly. Please check. If there is any problem in understanding, you can help. I'll help you out. Finished? Shall I go ahead? Right. Radhika, did you take note, beta? Right. Check out. The next type of hydrolysis which you will notice is from polyprotic acids. We check that from polyprotic acids. Okay. For example, if you have HX is monoprotic acid. Then H2X is diprotic acid. H3X is triprotic and HNX is polyprotic acid. This definition I told you earlier also. For example, if I take H2CO3, which is carbonic acid, if I take only 1 mole of NaOH, it won't be able to neutralize the complete H2CO3. Instead, first H2CO3 will convert into NaHCO3 plus H2O. So first one H plus will be neutralized with NaOH. But now the problem is, since there is no more NaOH left, if there is no NaOH left, you will only have this salt and water. Okay. Then you'll have only this salt and water. What if there is one more mole of NaOH present? In that case, you will have only this salt and water. So it depends upon which part of salt you are trying to hydrolyze. Are you hydrolyzing sodium bicarbonate? Are you hydrolyzing sodium carbonate? Now, we are mainly emphasizing this part, sodium bicarbonate. These type of salts which can undergo hydrolysis but also have at least one hydrogen left, which can act like an acid, which means it can be a proton which can still be released into the solution. That means it will make a dual role. It will act like a salt trying to hydrolyze water. That will anyway happen. Simultaneously, it will also act like an acid trying to release H plus ions into the solution. Correct? Such type of salts which has this dual role, which it can make hydrolysis also, at the same time it will dissociate H plus ions also. Such salts are called as amphiprotic salts. Remember the term amphiprotic salts. So salts which can act like acid due to the presence of proton but also undergoes hydrolysis. That is called amphiprotic salts. Now notice sodium bicarbonate, potassium bicarbonate, sodium bioxalate, sodium bisulfite, sodium hydrogen phosphate, disodium hydrogen phosphate, sodium hydrogen sulfite, sodium hydrogen sulfate. All of these forms are actually amphiprotic salts. These are all amphiprotic salts, which means they have at least one hydrogen present with them. Which can make it to act like acids. Okay. So let's try to understand how the amphiprotic salts, how to calculate the pH in the case of amphiprotic salts. Imagine initially the salt concentration is C naught. Amphiprotic salt concentration is C naught. I'm taking sodium bicarbonate as an example. You can do the same thing for other amphiprotic salts as well. So it will ionize 100%. So you'll get Na plus and HCO3 minus. So you'll have C naught and C naught value here. Got it? And now you notice this part here. So if you have CH3 COO minus plus NH4 plus, sorry, I'm saying this as HCO3 minus, HCO3 minus, correct? Which is what is acting like a strong base can interact with water and undergo hydrolysis. So if it undergoes hydrolysis, we can get H2CO3 plus OH minus. And hydrolysis constant, I can call it as Kh. As usual, we have done the derivation here. Now it has a dual role also. What is a dual role? HCO3 minus can also act like an acid to give H plus and CO3 2 minus. This is what you are expecting, correct? Now initially this is C naught concentration. Here also it is C naught concentration. Now what I'm assuming that from here some C naught H has been lost. So what will it form? C naught H, and C naught H will be formed here. And from here we have C naught H already lost. Along with that, it is losing some C naught alpha. So now this will become C naught alpha, C naught alpha. Now remember, H here represents degree of hydrolysis, degree of hydrolysis, while alpha here represents degree of second dissociation, degree of second dissociation, that is HCO3 minus. How does it dissociate? That is what we are talking about, degree of second dissociation. Got it? So from here I can write it as Kh is equal to C naught H, correct? C naught H into C naught H divided by, sorry, here since HCO3 minus concentration at both places will be same. So I can write it as C naught alpha here, minus C naught alpha. So I'll do one thing instead of writing in this term. So let me write in terms of their concentrations here. H2, CO3 and OH minus. That divided by HCO3 minus. While Ka2 here, because it is a second ionization, let me write it as Ka2. Ka2 will be equal to H plus into CO3 2 minus concentration divided by HCO3 minus. Now notice one thing, when it comes to H2CO3, you'll have H plus and HCO3 minus. Got it? Now you have C naught H here, correct? This one is C naught H here, and some amount of H plus concentration here. Here we will be having some small amount of H plus concentration, and HCO3 minus is of what amount here? C naught minus C naught H, C naught H minus C naught alpha. These are the values we have. So far, based on the given options, this is what we learned. What are all the equilibriums which are present? Can I write something here that Ka1 can be in terms of H plus into HCO3 minus divided by H2CO3. On the other hand, Ka2 we have already written that, sorry, Ka2 we have already written that, and Kw will be always equal to H plus into OH minus concentration. Now, observe it carefully. What if I multiply Ka1 and Ka2? What am I getting? Ka1 multiplied by Ka2. What do I get here? So you notice that this HCO3 minus and HCO3 minus will get cancelled, and you will be left with H plus whole square multiplied by CO3 2 minus divided by HCO3 minus, correct? So which means instead of taking any support from KH, if I know Ka1 and Ka2 values given to you, you can directly relate with the H plus ion concentration this way. And from here, I can write H plus concentration square is equal to Ka1 into Ka2 multiplied by HCO3 minus concentration divided by CO3 2 minus concentration. Correct? Please check, everybody. So far, all the equations are clear. Now, here is the interesting part. We will make one important assumption. That's a very important note. Assume that degree of hydrolysis, degree of hydrolysis and degree of second dissociation and degree of second dissociation is same. So if we assume these two are same, then what I can say, so the degree of hydrolysis, if you compare, that is how much amount of degree of hydrolysis we have here, that is H is equal to alpha. This is the assumption we are talking about. If you take that, now what will be HCO3 minus concentration? Go back and check the equations here. H, sorry, H2CO3 here. I made one mistake here. It should be H2CO3. This is H2CO3 concentration. Here also it is H2CO3. Yeah, right. So please check what is H2CO3 concentration here. H2CO3 concentration. Similarly, check out CO3 2 minus concentration. See, H2CO3 concentration is equal to, okay, SC0H, while CO3 2 minus concentration is equal to C0 alpha. So what do we have here? This is C0H and this is C0 alpha. And now, if you want to calculate the H plus concentration, so H plus whole square is equal to Ka1 multiplied by Ka2 into C0 H divided by C0 alpha. And you know that alpha is equal to H, so C0 will also get cancelled. Hence, it will be simply product of Ka1 and Ka2. So if I take the root on both sides, I will get H plus ion concentration is equal to under root of Ka1 multiplied by Ka2. So that makes it minus log of H plus ion concentration, which is equal to pH, and that is equal to pKa1 plus pKa2. So that will be the pH of the solution. Clear? Again, just like the last case, what we learned, where you have weak acid and weak base, here also pH is independent of initial salt concentration. So how much is the salt concentration does not make any difference in the value of pH. Clear, everybody? Now please go through it once. Let me know if you have a doubt on that. Whenever we do hydrolysis, correct? It's not like the compound will completely get hydrolyzed with water and form everything in products. There will be large composition of the reactant left. Only a small amount of hydrolysis is often observed. Correct. Similarly, HCO3 minus is a very, very weak acid. Since it's a weak acid, we can expect that there is a very small amount of dissociation also that we can observe. That means the equilibrium will be mainly staying on the backward direction. So whether you take this equilibrium or whether you take this equilibrium, in both of them, this is not going to be something where a product will be drastically forming in a larger quantity, which won't happen. That means majority of this and this will be present, which implies This is extremely small quantity. This is also extremely small quantity. Because the change is extremely small in quantities, we assume those quantities are tending towards almost the same value. Got it? Now, this is a calculus way of explaining. That means trying to explain that the limit tending to zero in the case of hydrolysis and limit tending to zero in the case of dissociation also. Correct? So since limit is tending to zero in both the cases, we assume both of them are equal values. Correct? Now, logical way of thinking is what? Check out. Suppose if I get any amount of H2CO3 forming, that will again dissociate itself into H plus and HCO3 minus. Can you see it is a loop, right? Whatever the amount this is forming, again it is trying to give back HCO3 minus. Is that clear? And the same thing goes with CO3 2 minus also. Because CO3 2 minus is even stronger base than uh, HCO3 minus, which means we can assume this is a stronger base. So it will again attach with H plus, trying to increase the concentration of HCO3 minus. So what have you noticed? That here also it is a loop reaction. So this is trying to, carbonate is again trying to make bicarbonate, correct? So here H2CO3 is also trying to make bicarbonate. And since it is in a loop value, you will see it will at a point, at an equilibrium point, you will notice that this, whatever it is trying to increase HCO3 minus, this would also try to increase HCO3 minus in almost the same quantity. That's why we assume that both the degree of hydrolysis and degree of dissociation is almost the same. All right. So you will not get very different answers as such or based on this assumption. So it is a very well approximated values you will get, correct? So this is an easy way of calculating out, especially for amphoteric salts. Okay. Now notice, what if you have amphoteric salt as another example? What if you have amphoteric salt as Na2HPO4? In the case of NH2PO4, correct? This is also amphoteric salt. And in an aqueous form here, that is Na2HPO4, in the aqueous form here, we expect that it will also dissociate into 2 Na plus HPO4 2 minus. Got it? And now it is the HPO4 2 minus which will undergo hydrolysis. Okay, so this is initial concentration C naught, and it will get completely dissociated into 2 C naught and C naught. So this C naught value, which is HPO4 2 minus, will react with H2O, trying to get itself hydrolyzed, which means it will become H2PO4 minus plus OH minus. So this will be the KH value. And on the other hand, HPO4 2 minus also showcases its acidic property by giving away H plus. So we will get this as PO4 3 minus. And this is the third dissociation of a phosphoric acid. So we write it as Ka3. And whatever the H2PO4 minus which is forming, correct, that will again ionize into HPO4 2 minus plus H plus. So this is Ka2 value. We do the same thing what we did earlier, multiply Ka2 and Ka3. Earlier we multiplied Ka1 and Ka2. Here it is Ka2 and Ka3. Hence we will get this as H plus concentration into PO4 3 minus divided by, okay, HPO4 2 minus. This is about Ka3 value. What about Ka2 value? This multiplied by HPO4 2 minus into H plus ion concentration, that divided by H2PO4 minus. Now you can clearly see that these two terms will get cancelled. and you will have this as H plus ion square into PO4 3 minus concentration divided by H2PO4 minus concentration. So from here I can write H plus whole square is equal to Ka2 multiplied by Ka3 multiplied by H2PO4 minus divided by PO4 3 minus. Okay. And again, this is the same assumption, that is degree of dissociation, degree of dissociation of H2PO4 minus and degree of hydrolysis of H2PO4 minus is same. Degree of dissociation and degree of hydrolysis is same. So in that case, this term and this term will get cancelled. So we will get this as H plus whole square is equal to Ka2 multiplied by Ka3. So hence pH will be equal to half of Ka2, sorry, pKa2 plus pK3. So this would be the correct answer, or much more closer values for the actual experimental amount. So this is how you calculate the pH. So I guess all of you understood this point. So the derivation is very much same as what we did for bicarbonate. There it was pK1 plus pK2 by 2. Here it is pK2 plus pK3 by 2.
Sir,
Yes, beta.
can you explain once why the assumption is made degree of dissociation, degree of hydrolysis?
Because both of them are extremely small values. See, dissociation degree of hydrolysis कितना हमने notice किया है? We took this as H is very very small value than 1, correct? And alpha is also very very small value than 1, correct?
Yes.
So we are assuming that these small values are almost the same. Hmm? Clear, beta?
Yes, sir.
So I guess all of you got that. Right. Notice this question now. Find the pH of 0.5 molar NaHS given Ka1 and Ka2 are given here. So what will be the value of pH? pH will be equal to half of pKa1 plus pKa2. So that is equal to half of pK1 is how much? 8 plus 14. Got it? That's all. We don't have to worry about what is the initial concentration given and all. Clear? So it is 22 by 2 and that is 11. So you can see it is greater than 7. So in most cases, pH value will be greater than 7 implies, okay, amphoteric, so amphiprotic salts are generally basic in aqueous solutions. So remember, okay, in organic reactions, organic reactions, Na2 NaHCO3, okay, is taken as alternative for small amount of base. So if you want a small amount of base here, then we can always use sodium bicarbonate as one of the source. You just need to add it in water, it will act like a basic solution. Yes, all of you are clear? Okay. Quickly go through the synopsis here. This is a complete synopsis of salt hydrolysis. Okay. I need a break for 5 minutes, everybody. Please go through it once. Let's start discussing about buffer solutions now. Okay. See, a solution which resists the change in pH is called buffer solution. That means if you have, let's say, a pH of particular solution is given, if by adding some amount of acid or base to that solution, if there is a drastic change in the pH of the solution, that means it is a normal solution. Maybe it is an acidic, basic, or some salt solution. But if it is a buffer solution, even if you add some amount of acid or a base, the change in pH is very minimal value. Okay. Such is what is called as, those type of solutions are called as buffer solutions. Now, there are two types of buffer solutions. One is neutral buffer, the other one is mixed buffer. We use the term neutral buffer only for one salt form. That is, when you have weak acid, weak base. If you have weak acid, weak base combined salt, correct? This solution can act like a buffer. Okay. If you take this salt solution, let me tell you how. Suppose if you add HCl, then CH3CO minus will try to consume that H plus and convert into undissociated CH3COOH. If you add OH minus, NH4 plus will consume all the OH minus and convert into undissociated NH4OH. That means neither the H plus nor the OH minus is spiking up on adding some extra HCl or NaOH, correct? So what is it doing? It is trying to balance the pH of the same value what it was originally present. Clear, everybody? So that's why these type of solutions are called neutral buffers. Next, see what is mixed buffer. Mixed buffer is when you have either two forms, an acidic buffer or a basic buffer. Here, an acidic buffer implies it should be a weak acid combined with a conjugate base salt. Weak acid like CH3COH combined with conjugate base salt, which is CH3CO minus, that is a conjugate base salt. Next, basic buffer. Basic buffer is weak base combined with conjugate acid salt. Weak base is NH4OH and its base salt is ammonium chloride. Okay. So when you have an acid, weak acid, and its conjugate base, both of them are present. Similarly, if you have base, weak base, and its conjugate acid is present, such kind of solutions lead to formation of buffer. If it is out of the weak acid, we call it as acidic buffer. If it is made out of the weak base, we call it as basic buffer. Just by watching the mixtures, you should be able to assess whether they are buffer solutions or not. Everybody, correct? So let's notice one by one and see whether it is buffer solution or not. For example, HCl combined with NaCl. HCl is a strong acid, NaCl is a normal salt. So is it a buffer? Definitely not. Because idea is for a mixed buffer, we need to have at least one weak species, either weak acid or a weak base. None of that is present here. So it cannot act like buffer. See the second one. When it comes to the second one here, see HCOOH, weak acid, HCOO minus, that is conjugate base of the same weak acid, and that is the essential condition. So this is fulfilling that. So it is a acidic buffer. Clear? Next, ammonium sulfate salt, H2SO4, strong acid. Strong acid does not fulfill our need. So what is this one? This is not a buffer solution. Correct? Next, ammonium sulfate salt and ammonium hydroxide. Ammonium hydroxide is weak base, and this weak base also has ammonium ion, which is a conjugate acid present in the solution. Hence, yes, this will be a buffer solution. Which buffer? Basic buffer solution. Likewise, HCl, a weak acid, and Cn minus, Na plus and Cn minus. Cn minus is a conjugate base. So yes, this is also a buffer solution. Next, Na2S reacting with H2S excess. Now notice this one. If you have something like S2 minus, which is in excess, plus H2S. So what do we expect? That we expect this S2 minus will take away one H plus and convert into HS minus. Since this is limiting reagent, that is, this is limiting reagent and this is excess reagent. So this will not be left in the solution. After some time, this will not be left in the solution. What is left in the solution is H2S and HS minus. And you know that H2S is a weak acid and HS minus is a conjugate base salt. Hence, this is a buffer solution. So yes, this is a buffer solution. Likewise, NaSH. NaSH is HS minus. That is HS minus. HS minus is an acid, weak acid. I can still consider HS minus as a weak acid because it still has one hydrogen present with it. And S2 minus is a conjugate base of this weak acid, correct? So this combination also perfectly fits. So this is also an acidic buffer. Ammonium chloride, but HCl. HCl is a strong acid. Hence, this cannot fit into the buffer solution. Correct? Next one. Ammonium hydroxide, weak base. Ammonium chloride, conjugate acid present in it. So yes, this is a basic buffer. Okay. Next. CH3COOH, weak acid, good. But is this a salt? No, this is an organic compound, a different compound. Salt should be like this, CH3COO minus. That is not the one which is there. It is a compound called acetyl chloride. So this compound is not a salt form or a conjugate base form of acid. Hence, this is not a buffer solution. Next, CH3CO minus, it is a salt coming from a weak acid. Perfect. But it is given with KOH. KOH is a very strong base. So this is not a right combination. Last, weak acid, you can see here, it is a weak acid and this is its conjugate base salt. So yes, this is a perfect combination. So check it out. Clear everyone? So always try to check these points, that whether it is a weak acid, weak base, what is the type of salt that is present along with it. Okay. So now let's see. If you have an acidic buffer, correct? If you have an acidic buffer, then it means we will have a weak acid and a conjugate base salt present in it. Let me take one example here. For instance, if you have a combination of CH3 COOH with CH3CO minus Na plus salt, correct? Concentration wise, let's say the concentration of acid is A, concentration of salt is S. Now we know that CH3COOH, right? In the aqueous solution, it will ionize into CH3CO minus aqueous plus H plus. This will be the Ka value for it. But notice one thing, initially, while it is ionizing, already there is a salt present, isn't it? Already there is a salt present because this is the salt ion concentration. So now at equilibrium, assume that some small amount of acid is dissociated here to get S plus X and X, correct? So from here I can write Ka, which is equal to concentration of CH3COO minus multiplied by H plus concentration divided by CH3COOH. And from here, H plus concentration can be written as Ka multiplied by CH3COOH divided by CH3COO minus. This is what you will have. Correct? Now notice, what if I take minus log on both sides? So we will get this as pH is equal to pKa plus log of, minus log of. So minus log of CH3 COOH concentration divided by CH3 CO minus concentration. Now notice CH3 COOH concentration is equal to A minus X and CH3 CO minus concentration is equal to S plus X. Now listen, this is a very weak acid. Already it is a weak acid, its dissociation is less. On top of that, what if it already has a common ion? Because of the common ion, the equilibrium mainly, stays in the backward direction, which means the dissociation that it happens to be a very, very small extent. Hence, I could say X value is way, way smaller than 1. Thus, this can be equated as A, this can be equated as S, because I'm ignoring X in both cases. Hence, how do we write pH? Now, pH can be written as, pKa minus log of acid by salt concentration, or simply pKa plus log of salt by acid concentration. So this equation which we write, which is pH is equal to pKa plus log of salt by acid concentration. This is what we call it as Henderson's buffer equation or formula. Buffer formula or buffer equation. So for any weak acid combined with its salt making a buffer, for that the pH value can be calculated like this: pKa plus log of how much is the salt concentration divided by how much is the acid concentration. Clear, guys? Okay. Now, please, I hope all of you made a note of it. Okay. If you are aware of the derivation, at least write the formula. Right. Check now. How do you solve the questions regarding that? Check this out. 400 ml of zero point 0.1 molar HCOOH is treated with 100 ml of zero point 0.1 molar NaOH. Let's say it is an acid base. So how does the reaction take place? HCOOH plus NaOH. Expected is a salt, which is HCO minus Na plus H2O. This is the expected reaction. And you have this as 400 into zero point 0.1, which is millimoles, and 100 into zero point 0.1 millimoles. So initially, how many moles we have? Here we have 40 millimoles. Here we have 10 millimoles. Okay. So you can clearly notice that this is limiting reagent, this is excess reagent. Therefore, this 10 millimoles will be consumed. So here, out of those 10, if I remove this, we'll get 30 millimole left. And what about the product? This was initially not there, but now because of the limiting agent, so 10 millimoles will be formed here. Correct? So this is the form. So this is the left amount here. This is the amount of the salt formed here. Okay. So now in the resultant solution, there is no NaOH. You have a weak acid and you have its conjugate base salt. Isn't this what we call it as a buffer? Correct. So it is a acidic buffer. Therefore, the solution make up make up for an acidic buffer. Since it is acidic buffer, you have to calculate the pH value. So pH is equal to, you can calculate the pH value using the formula pK plus log of salt by acid concentration. Now salt concentration is equal to 10 millimoles divided by total volume, and acid concentration is equal to 30 millimoles divided by total volume. And since you are taking the ratio, this total volume term will always get cancelled. So we don't have to worry about what is the total volume at the end. Hence, you can see pH is equal to pKa value. pKa value is given as 3.8 plus log of salt concentration, which is 10 by acid concentration 30. So 3.8 minus log of 3. Okay, so because it is 1 by 3, so it is minus log of 3. So that is coming out to be approximately 3.33. So this will be the pH of the solution. pH is equal to 3.33. So I guess all of you understood how to calculate the pH in the buffer solution. Okay. Please make a note if you haven't done it. Right, everybody. Check out the second case now here. Second example. 400 ml of 0.1 molar CH3COH is treated with 50 ml of 0.1 molar barium hydroxide. Again, you can write the equation what is happening. CH3COOH plus barium hydroxide. The reaction what you are expecting is CH3CO twice barium plus H2O. Balancing wise, we should always have two of them here. So it is 400 cross zero point 0.1 and here it is 50 cross zero point 0.1, which makes it 40 millimoles here, and here we have 5 millimoles. Okay, so you can notice that for every 1 mole of barium peroxide, barium hydroxide, we require 2 moles. For 5 require 10 moles. So you can see 10 moles are being required. So the leftover moles are 30 millimoles. And barium hydroxide is the limiting reagent. And you can see for every 1 mole, I'm getting, 1 mole of salt. So for 5 millimoles, I'll get 5 millimoles of salt. You'll get 5 millimoles of salt. And you know that CH3CO minus, twice barium here, that will again ionize to form 2 moles of CH3CO minus plus Ba2 plus. So which means this 5 millimoles which it has formed, basically this entire thing will again ionize to form 10 millimoles of acetate ion and 5 millimoles of barium, which means the salt ion concentration is 10 millimoles. And that's what we require, right? So this is that factor S. This is that value S. And here, this is the value of A, that is acid concentration. So what is the formula? pH is equal to half of pKa value, which is 5. Right, sorry. pH is equal to pKa plus log of salt by acid concentration. So pK value is 5 plus log of salt is 10 divided by 30. So we're getting the same value, 5 minus log 3. Correct? Same as above. Above we had only 3.8, now we have 5. Clear? So we have this as 5 minus log 3, which is 4.52. Everyone clear with this part? So here stoichiometric, errors will be made. So be careful with it. Usually, many of the students will take 5 millimoles as the salt concentration. That is incorrect. It should always be 10 millimoles because it is not the salt ion we are talking about. Sorry, it's not the salt concentration we are talking about. We are talking about the salt ion. So therefore, you need to check out how much is the ion concentration. Done. Right. See, if you talk about basic buffer, the idea is the same. Okay. We need to have a base, weak base and its conjugate base salt. Got it? Done. So let me take a weak example here. Let me take a weak base example, that is ammonium hydroxide. That when you combine with ammonium chloride as a salt, so this is acid concentration. Sorry, this is base concentration, and this is salt concentration S. Okay, the equations will be very similar to what we have worked out for acid solution, acid buffer. That is, we will have NH4 plus and OH minus maintained at equilibrium with Kb, right? And if this is B, right, this is S and 0. So this will become B minus X, S plus X and X. Same logic, P, you will get this as OH minus concentration. OH minus concentration is equal to Kb multiplied by NH4OH divided by NH4 plus. Now if I take log on both sides, you'll get this formula. POH is equal to pKb plus log of salt concentration, which is NH4 plus concentration, divided by NH4OH concentration, which is base concentration. So this is another formula for Henderson's equation or Henderson's formula, which is log of salt by base concentration. This is also termed as Henderson's equation. But this equation is for basic buffer. So nothing new, derivation is exactly same. See how the questions are framed here. Look into this question. Very easy ones. 800 ml of zero point 0.2 molar NH4OH is treated with 100 ml of zero point 0.2 molar H2SO4. Find the pH of the final solution. Okay. So basically the reaction is happening like this. 2 moles of NH4OH plus 1 mole of H2SO4. We are expecting this to form. Sorry. Making an acid-base reaction. We are expecting this to form ammonium sulfate plus H2O. And now this was 800 into zero point 0.2 molar. This is 100 into zero point 0.2 molar. Clear? So here we have around 160 160 millimoles, while here we have 20 millimoles. You know that for every 1 mole we require 2. For 20 millimoles we require 40. So minus 40 millimoles. So that makes it 120 millimoles left. So this one is the left amount of base what you have. So H2SO4 is not left over, and 20 millimoles will give you 20 millimoles of the salt formed, but not the salt ion, which you can clearly notice from here that when it comes to ammonium sulfate, that also will ionize into aqueous solution to form 2 moles of NH4 plus and SO4 2 minus. So if this is 20 millimoles, so this entire thing will convert into 40 millimoles of ammonium salt and 20 millimoles of sulfate. And POH will mainly have pKb plus log of salt by base concentration. So pKb here value is 5 plus log of salt. Salt concentration here is not 20, it is 40. It is the salt ion concentration that you should be more interested in. So that divided by base concentration, which is 120. So hence it is 5 plus log of 1 by 3. So you can see again you are getting the same value, 5 minus log 3. So just now we got that value, 5 minus log 3. How much we got? 4.52. So we'll get this as 4.52. So that will be the POH value. Check everybody. Once you know the POH value, a lot of time the question is not asked in POH, it is always asked in pH. So pH will be equal to 14 minus 4.52, so which is 9.48. So that is the pH value. So these are very basic questions which you need to know how to solve it, buffer solution cases, especially for acidic buffer and basic buffer. Here everybody. So right, so we'll stop it here as much as the buffer solutions are concerned.